So for this lecture, we will discuss extensions of the classical Lax-Milgram lemma, and by relaxing some of the conditions of that result. So here the theorems will be stated without proof. Nevertheless, some examples will be provided. So the first one is the Lax-Milgram Fredholm lemma. So the idea is to replace the coercivity condition by some condition. So the statement of this result is as follows. So now we have, let's say, two Hilbert spaces, say V and H. And this V is a subset of H, and this is dense and compact. So this means that the closure of V, okay, with respect to the topology of H is H, and compactness means that if Vn is a sequence in V is bounded in the topology of V, then we can obtain, or we can have a subsequence V and J such that this V and J tends to V, or let's say U, for some, the convergence is taken with respect to the topology of H for some limit U in H. So any bounded sequence in V has a convergent subsequence in H. That is what we mean by compactness of this subset or this inclusion. Moreover, let us consider two bilinear forms. So A sub H, this is bilinear and bounded. And another bounded bilinear form, A sub V. This is bilinear, bounded, and coercive. Then, for this problem, so the variational problem, let's say AV of XY plus AH. Well, let us change annotation. Say UV plus AH UV equal to the duality pairing FV, V prime cross V, for all V in the Hilbert space of V has either a unique solution U in V for every F in the dual space of V, or a non-trivial solution U in V for F being the zero functional. Okay, so here our left-hand side, the bilinear form is not necessarily coercive. So it is coercive plus some bounded perturbation on a larger space. So here, A sub h is the perturbation or the uh, difference between a bilinear, bounded, and coercive form. So your form on the left-hand side is not necessarily coercive, but it is coercive plus some bounded bilinear form on a larger space H. Okay, so in terms of, let's say, in the case of a finite dimensional square systems, you can think of this as what? So either your matrix is invertible or it is not injective. So therefore, you will have a non-trivial solution for your homogeneous problem. So as an example, let us revisit the boundary value problem with an additional convection term. So now our problem is the following. So divergence of A times the gradient of U plus some vector valued function B is responsible, let's say, for convection plus C of X, U of X for X in omega, and still the conormal derivative is 0 on the boundary. So we want to find, let's say, a function U that satisfies this property. Again, here, omega is a bounded, open, connected domain with a sufficiently smooth boundary. The given data now is the following. So A is essentially bounded matrix valued function. And this is coercive or elliptic, let's say. As before. And a C is essentially bounded, but we do not assume that it is bounded from below by a positive number. H is L2, and B is a non-zero vector field with essentially bounded components. So these are the given data for this problem. Now, utilizing the same process as before, an H1 function, U is called a weak solution. If the following variational problem is satisfied. So you mimic the process and obtain the following variational problem. But now with the additional convection term. Still, the test functions are located in H1. So this is a weak solution of our second boundary value problem. And here we will show that our boundary value problem has either a unique weak solution for any h in L2 omega, or as a non-trivial weak solution for h equal to 0. Okay, take note that in this case, when h is 0, and if c is 0, okay, this two terms here will vanish, then any constant function will satisfy this boundary value problem. Therefore, you have a non-unique solution here. And also a non-trivial solution. And this is our claim. And based on this statement, it is enough to apply the Lax-Milgram-Fredholm lemma. So as usual, we need to define what are the Hilbert spaces V and H. So V would be our solution or the test space. So that would be H1, and H would be the L2. Okay. First, it is known that, okay, so let me state without proof. So it is known that the embedding of H1 into L2 is dense and compact. Okay, so this is an essential part of the Lax-Milgram-Fredholm lemma. So let us accept this statement at this point with faith, and we proceed with the proof. So the next is to split the bilinear form on the left into two parts. So the first one would be the following. So A sub V of, let's say, U phi this would be the same left-hand side, almost the same left-hand side. But then we need to, let's say, add some term beta. My plus C, okay, U phi. Where beta is a positive parameter, this will be chosen later. And since we need, we added this term, we need to subtract that. So we will have the negative of the integral of beta U phi dx. And likewise, we define, let's say, f from V to R as follows. So f of phi to be the right-hand side of your variational problem. Okay, then it's now clear that our variational problem here can be written as the sum. So let us write this as VP2 this is equivalent to AHU phi plus let's start with AV. Okay, AVU phi plus AHU phi equal to F phi. So here the rest function is also in H1, so that is UB. So again, we are now in the framework of the Lax-Milgram Fredholm lemma. So as before, the linearity of the integral and applying the Holder's inequality, you can show that AH and AV are bilinear and bounded. And likewise, F is linear and bounded. So it remains to verify the coercivity of A sub B. So for this, let us take a U in H1 and let us estimate from below this bilinear form evaluated at U. So first, let us plug in the definition. Of your bilinear form. U squared dx. And now applying Holder's inequality. This one is and applying the ellipticity of A. We get the following, similar as before. So you have alpha times the L2 norm squared of the gradient minus the L infinity of your vector field times the gradient norm, okay, squared times the L2 norm of U. Okay, we should not have a square there. So you apply here the Holder's inequality. And for the last term, you have beta minus the L infinity norm C times the L2 norm squared of U. So the crucial part here is estimating the second term. And for this, we apply the Young's inequality for real numbers. So that is when you have AB non-negative, okay, and a positive epsilon. If you want to estimate the product The product, let's say, of AB, you can write this as square root of epsilon A times 1 over square root of epsilon B. And then you apply the Cauchy-Schwarz inequality to obtain epsilon over 2 squared plus 1 over 2 epsilon B squared. So this is Young's inequality. So the basic idea here is that we can put a small factor, epsilon, on one term at the expense of a larger factor on the other term, or on the other square. So applying this Young's inequality and multiplying both sides by negative. So you take this to be your A, and then you take this to be your B. We can continue and obtain the following. So you have alpha times the gradient of U, L2 norm, the gradient of U, minus, so here we want to put a small factor on the first term. And then minus 1 over 2 epsilon times the L2 norm squared of omega. And adding that to this term, so this is the final term in the above inequality. Okay, so we can now simplify this as follows. So alpha minus 1/2 epsilon times the L infinity norm of B plus beta times the minus the L infinity norm of C minus 1 over 2 epsilon. So take note here that these terms corresponds to the square of the H1 norm of U. So I want this to be, okay, so let us denote this by a C sub 1 and this by C sub 2 for simplicity. And I want this to be both positive. So what we do is we first choose epsilon is small enough such that the first term is positive. So that would be epsilon would be less than alpha divided by or 2 alpha divided by the square of the L infinity norm of B. So here the denominator is not 0 because we assume that B is not a 0 almost everywhere. And we then take the parameter beta after choosing epsilon to be greater than L infinity norm C plus 1 over 2 epsilon. So the idea is to put a small factor on the gradient in order for the coefficient of the gradient norm would be positive. And from this, after choosing epsilon, we now choose the parameter beta. Okay, so with this, we are now we now have the following lower bound. So you just take the minimum between C1 and C2. So based on the choice of epsilon and beta, these are both positive. So this is also the minimum. It's also positive. Times, well, the sum of the squared with the L2 norm of U, and the L2 norm of the gradient is nothing but the H1 norm, but H1 is, we denoted this by V. And this establishes the coercivity of V. Therefore, going back to our problem, our boundary value problem 2 has either a unique weak solution for any H in L2 or has a non-trivial weak solution when H is 0. So far, we have discussed variational problems wherein the space where the weak solution are located is located and the test functions are located are the same. And this is also the case of the Lax-Milgram lemma and the Lax-Milgram-Feldholm lemma. So the function spaces for the weak solution and the test functions are the same. In certain scenarios where the weak solution space and the test space are different, the following generalization of the Lax-Milgram lemma can be utilized. And this is called the Banach-Necha's-Babushka theorem. So to state this theorem, let us consider again two Hilbert spaces. So you can think of here U as the solution or weak solution space and V as the test space. And I have a bilinear form on U cross V. So bilinear, bounded, and we have the so-called in-sup condition. So the infimum over all non-zero U in capital U of the supremum over all non-zero V in capital V of AUV divided by the norm of U times the norm of V is greater or equal to some positive constant C. And this is true for any, it's true for some positive constant C. And finally, we have injectivity. And by this, we mean that if AUV is equal to 0 for all V in your Hilbert space V, then U must be 0. If these conditions are satisfied, then for every F in the dual space of V, there exists a unique U in capital U, wherein AUV is equal to the duality pairing for all V in the test space capital V. And similar to the coercivity, or I should say the Lax-Milgram lemma, we have stability of solutions. So the norm of the solution is less than or equal to 1 over C. So that's the constant in the inf soup condition times the norm of your data F. So here, your bilinear form is defined on different function spaces. The components are defined on different function spaces. And as a replacement of the coercivity condition, we have this inf soup condition and this injectivity condition. So here, the solution space is different from the test space. So as an application of this theorem, let us consider the instationary heat equation. So the problem is to find a temperature distribution. Now, your function depends on time, satisfying the following heat equation, HE. So the change in the distribution is proportional to the diffusion plus some, let's say, some sort of a damping term, and then the heat source. So here, our functions are now time dependent as well. So for Tx in 0t cross omega, and omega is smooth domain, and the final time capital T is positive. We also assume that the conormal derivative is 0 for Tx in the time interval cross the boundary, and assume that the initial temperature distribution is 0 for x in omega. Okay, so with this, we now define the concept of weak solution to this problem. And again, this definition is obtained starting, let's say, from a smooth solution and then integrating by parts to after multiplying the appropriate test functions. So first, the Laplacian here is the negative divergence of the gradient. So you can think in our stationary heat problem discussed previously, you can think of the matrix A to be the identity matrix. So to set up, let us define our solution space. Since for a given, let's say, fixed time, if you fix time, you have a function with respect to x. So for this problem, we now consider the Lebesgue-Bochner spaces. So we take U to be the set of all L2 functions defined on the time interval 0 to t with values in H1. Omega. Wherein U of 0 is equal to 0. So here we append the initial data. And of course, we need that this one, the time derivative, is also in, let's say, L2 so the time derivative is square integrable, but it has values in the dual of H1. So for the test space, we apply this subspace. I would like to note here that U is contained in V. So the test space is larger than the solution space. So with this annotation, an element, let's say U, in capital U, is called a weak solution of our heat equation if the following variational equation holds. So what we do is we test by V and then integrate by parts. Applying again the divergence theorem, we get the following. So now we have here an integral from 0 to t. The time derivative times the test function. So here we now have the duality pairing. Plus the H1 inner product of U and V. Okay. That would correspond to these two terms. So here you will get the gradient of U dot gradient of V dt times the duality pairing of HT VT and here we have here the duality pairing as well. This is for all U, or I should say for all V, in this function space. So that this is basically, according to our notation, capital V. And here the given data is in V prime, which is can be shown that this is isomorphic to the Bochner space L2 0T H1 prime. Okay. So this is our definition of a weak solution. So the idea is to multiply this by V, both sides, or more precisely, take the duality pairing. And for this, you integrate by parts. And with that, you will get the H1 norm for these two terms. So I will leave the details for you to write that down. So before we proceed, let us emphasize here that U and V are Hilbert spaces with respect to the following inner products. So the inner product in U will be the following. This is basically the L2 inner product of the two functions with respect to this Bochner space, as well as the time derivatives. And similarly for V, we take the first term only. In fact, we can provide an alternative representation of the inner product in V using the Riesz representation theorem. So let us denote by R the Riesz map between H1 and its dual. Recall that this is an isometric isomorphism. So with this, we now have the following. So the L2 inner product of V1 and V2 would be, okay, so writing in terms of the integral. So the definition of the inner product in L2 0T H1 is this. And on the integrand, we apply the Riesz map. So now instead of V1, we take, instead of having this inner product, we have this duality pairing. Okay. So with this, we can write. We can also replace this term here by the Riesz map. And therefore, this variational problem is equivalent to the following. So you replace the inner product in H1 by the duality pairing thanks to the Riesz map. So it would be AUV. This AUV would be the left-hand side. So here you now have the Riesz map, V of D. Okay. So from now on, this duality pairing, for simplicity, will be duality pairing with respect to this function space. And we will not emphasize the subscript anymore for simplicity. should be equal to this FV V prime V, and this is the integral of h of t v of t, the duality pairing in h1 prime in h for all v in capital V. So we have written our problem in the framework of the BNB theorem. So let us now prove the desired conditions. So first, it is clear that f is linear. Aha. So let us see here. So this should be, I should say h. So let us replace this by hv, since that is our data. So we already know that h is in v prime, a is bilinear. You can easily show this using the linearity of the derivative or the weak derivative and the linearity of r. And the linearity of the duality pairing with respect to both components, as well as the linearity of the integral, the Lebesgue-Bochner integral. For boundedness, okay, so for any u, capital U, and v in capital V, so applying the Cauchy-Schwarz inequality, you will have the following. For the first, you have the L2 norm of the time derivative with values in the dual of h1 plus, okay, applying the fact that R is an isometry, okay, so it does not, so it preserves the norm. In this case, you will have this norm of U times the L2 norm of your test function. Okay, so each of these terms is obviously less than the U norm. So you have the twice of the U norm times the V norm of V. So this establishes the boundedness of A. Now for injectivity, so suppose we have a uv is equal to 0 for any v in capital V. So we wish to show that u must be 0. So if we take a specific v, so taking v, of course, here u is in capital U. So if we let v to be u, U is in capital U, and we know that U is a subset of V, so this is admissible. Then we have the following. So this is equal to, let's say, applying the definition of A, dt ut. Here we apply the first definition, of course. So times ut, the duality pairing, plus the L2 inner product of ut and itself. So that would be this one. Dt. And then it can be shown that integrating by parts, we end up with the following. So here it can be shown that this is 1/2 of the L2 norm, okay, squared, evaluated at t equal to 0 and t equals capital T. So now here you have the L2 norm of the time at the final time. Okay, since we know that u of 0 is 0 by the definition of capital U. And they note that this is well defined since it can be shown that U is embedded in the space of continuous functions on the closed interval 0 to t with values in L to omega. So this requires some technical details, but let us accept this is indeed the case. So function evaluation with respect to time is well defined, but now the values are in L2. And this has something to do with Gelfand triples, which we hopefully discuss in future lectures. Okay, so from this, we now obtain the following equation. So plugging this value in the previous equation, you have the following. And this implies, of course, this is possible only when u is 0 in V, or in, I should say, yeah, in V, hence in U. So this establishes the injectivity condition for your bilinear form A. And finally, for the inf sub condition, you start with an element U not equal to 0. And let us define another element, let's say W. This is R inverse of DTU plus beta U, where beta is a positive parameter. Where beta is a positive parameter to be chosen later. Then after some details, it can be shown that W is non-zero. So if W is zero, this would imply that U is zero, which is a contradiction. And applying the fact that hence R inverse is an isometric isomorphism, W is also in V. Okay, and we can estimate the L2 norm of a W. So this is less or equal to the L2 norm of the time derivative, but now taken in the dual space of H1. Here we use the fact that R inverse is an isomorphism from H1 omega prime to H1 omega plus a beta times the L2 norm. In H1. Okay, so this is what? Less than the max of 1 and beta of the so probably we can put a factor 2 twice the max 1 beta of the U norm of small u. So you can apply the definition of, take note that these two terms are less than, both less than the U norm. Okay. So you have this estimate. And for simplicity, let us define this to be C. And in particular, we will have the V norm of W is less than or equal to C times the U norm of U. Okay, so from here, let us now estimate from below AUW. And this is, okay, applying the definition of A. And applying the definition of W. And after some details, namely applying Young's inequality, as well as the fact that R is an isomorphism, one can show that this is one minus epsilon over 2 times this integral plus, okay, beta minus 1 over 2 epsilon plus 1/2, or I should say beta over 2, and then applying the same argument here for this two duality pairing, namely this term can be obtained from these two components. So we have beta over 2 times u of t squared. So again, here we choose first epsilon to be less than a half, and then choose beta to be greater than 1 over 2 epsilon. If we set, let's say, delta to be the minimum, between 1 minus epsilon over 2 and beta minus 1 over 2 epsilon. This is positive according to the choice of epsilon and beta. Then we have AUW is greater or equal to delta. So you take the minimum of the two, that would be delta. You take the sum of this, and this is basically the U norm. And since this is non-negative, we can ignore this term. So this is greater or equal to the U norm of U squared. So here, take note, this is almost coercivity. But then, of course, the difference that here you have a different argument. And let us write this as follows. So we split U into two parts. And then for the first, or for the second, we apply the fact that, that the U norm is greater or equal to 1 over C times the V norm of W. So you use that. To obtain this. And therefore, we can now estimate AUW divided by the U norm times the V norm of W. This is greater or equal to delta over C. Delta is positive and C is also, of course, beta is chosen to be positive. So C here is also positive. So this is positive. Take note that this is, of course, less than or equal to the following. If you take the sup overall non-zero V. So here we took a specific V, namely W. And we said that W is non-zero and it's also an element of V. And I take note that this is true for any U in capital U. So since this is valid, taking the infimum over all, of course, U not equal to 0, over all non-zero U, we get the desired inf sup condition. So that's the inf sup of AUV divided by the norms of the arguments. This is now greater or equal to delta C. So to summarize our bilinear form, so going back, so our bilinear form is bounded, disinjective, and it satisfies the in-soup condition. And therefore, we can apply the Banach-Netschas-Babuška theorem to establish the existence and uniqueness of the weak solution for the heat equation, as well as the stability condition as well. The statement that W here is not zero can be derived as well with this inequality. Take note that if W is zero, the left-hand side would be zero, and that would imply that U is zero as well, which is a contradiction. Okay. So that's the application for the Banach-Netschas-Babuška theorem. So far, we have discussed examples of elliptic and parabolic partial differential equations. So the heat equation is a prototype or an example of what we call a parabolic differential equation. In the case of hyperbolic PDEs or ODEs, for instance, the wave equation, one can use the following theorem, the Lax-Milgram Friedrichs. So to state this, let us consider two Hilbert spaces, X and Z, and a subspace Y of X. Suppose that we have three linear operators, all are mappings from Y, the subspace, into a Z. These are linear, wherein the kernel of phi is non-zero, and the image of the kernel under phi is also non-zero. So these subspaces are non-trivial. So in terms of applications, you can think of this as lambda as your differential operator, your psi would be your, let's say, your boundary, and initial conditions. For the solution, and phi would be the, say, the boundary and initial condition for the test function. So you can think of these operators in this way. Now, suppose I have a bilinear form on X that is bounded and coercive. So for coercivity, more precisely, A of X is greater or equal to some positive constant alpha times the norm of X for all X in capital X. And moreover, one can find a positive beta such that with respect to the operators defined above, the X norm of Y plus the Z norm of psi Y is less or equal to beta times the X norm of lambda Y. Okay, so there should be a correction here. This should be X. Plus the Z norm of phi Y. And this is true for any Y in the kernel of phi. If these conditions are satisfied, then the solution, or given f in the dual of x prime, the dual of x, and g in the dual of z, there exists a solution x to this variational problem. Ax lambda w equal to, here we have the duality pairing on x plus the following duality pairing in z. And this is true for any test function w in the kernel of phi. And here, this should be replaced into the subspace Y. Furthermore, the solution is unique if and only if the image of the kernel of phi under lambda is dense in X. So in contrast to the Lax-Milgram lemma, here we have two Hilbert spaces and another subspace of X. So X here is your solution space. You can think Z as your function spaces for the initial conditions, and Y can be taken as a subspace of your test or the space of test functions. But more precisely here, the test functions are taken not with Y, but on a subspace, namely the kernel of phi. So to illustrate the application of this theorem, let us consider the following example. Let's say we have linear impulsive ODEs. So here, the source terms for the ODEs will now be point sources. Okay? And to be more precise, we consider the following. So we consider the following linear impulsive ODEs. And let's say this is U prime plus AU equal to H in a finite interval, time horizon 0 to t, and some initial condition U naught. So the unknown function here is U. And let us consider the K subsistence. So this is a function from 0 to t with values in Rn. The given data here is that H is in L2, and the initial condition U naught is a vector in Rn, and A is, let's say, it is essentially bounded matrix valued function. Okay, let us replace this. So H is not an L2 function since it involves sources. So let us define H as follows. So H is an element of the dual of H1 to the n. Okay, so you have n components, and more precisely, it is given as follows. So H, let's say, it is a linear combination of Dirac functions, or Dirac measures. So K here, we range from 1 to m. C sub k's, or C sub 1 to C sub m, are vectors, and the time samples T1 to Tn belong to the time interval 0 to t. So they may include the initial and final times. So more precisely, the duality or the action of H on W, or any W in H1 would be the following. So this is the linear combination of the dot product of the coefficients C sub k, and then you evaluate W on the time samples. So here the inner product is taken with respect to the inner product in Rn. Well, this is well defined since it can be shown that this is isomorphic to the set of absolutely continuous functions on the closed interval 0 to t. So in particular, these functions has representative that are continuous. Therefore, function evaluations at certain time samples are well defined. So now we are in position to define what do we mean by a weak solution. So here we take L2 functions. So a vector value, the L2 function, is said to be a weak solution of our linear impulsive ordinary differential system of ordinary differential equations if the following variational equation holds. So again, the main idea is to test this with W, okay, and integrate by parts, meaning we pass the derivative with respect to the test function. So performing that, one can obtain the following. So the negative sign here is due to the integration by parts formula. And here we take the transpose of A. dt equal to hw. So integrating by parts will give you boundary terms. So this would be the time t equal to 0. And for the terminal time, let us say that our test function would vanish at the terminal time. Therefore, that will yield no contribution for this variational problem. Okay. So this is our notion of weak solution for this impulsive linear ODE. So what we do is we translate this in the framework of the Milgram Friedrichs theorem. So we need to state what are the Hilbert spaces X, Y, and Z. So our solution space is L2. The function space where the test functions are located would be in H1, and Z would be Rn. Okay, so with this, we also have our differential equation, lambda, applied to the test function. So lambda would be negative W prime. Here, prime denotes derivative with respect to time, plus A transpose W, psi of W. As we said a while ago, psi would be responsible, so going back here, psi would be responsible for the initial condition for our solution. So this would be W of 0. And likewise, 5t W, this would be the one that is responsible for the test functions. So this would be W of t. So in particular, the kernel of phi will be the space of H1 functions where the value at the terminal time is 0. And this is precisely the characterization of test functions here. Okay, so based on this, our variational problem. Okay, but first we need to state what is A. A is basically the L2 inner product. And let us denote by, let's say, R sub Z, the risk map from Rn into its dual space. With this, our variational problem can now be written equivalently in the framework of the Lax-Milgram Fredholm theorem as follows. So we have here the inner product. So this is namely the inner product. So that would be A U lambda W equal to HW. Okay. So take note that H is in the dual space of H1. So that's Y prime Y plus here we apply the risk representation theorem. This is R Z of U naught times psi of W. And this second duality pairing is taken with respect to Z. And for all, should be valid for all W in the kernel of phi. And take note that this RZ is an element of Z prime. Because U naught is in Rn, so therefore the image under the risk map is in the dual of Rn, but Rn is Z. Okay, so we have now written the variational problem for our linear impulsive ODE in the context of the Lax-Milgram Fredholm theorem. So it is clear that lambda, psi, and phi are what are linear. The kernel of phi is non-trivial, and the image is also non-trivial under lambda. So it remains to verify the third condition here. Without going into the details, that condition is in fact valid due to the following Poincare type inequality. And it can be shown that for all, or there exists a beta greater than 0, such that for all W in H1, the L2 norm W plus the Euclidean norm W0 is less than beta times negative W prime plus A transpose W plus the Euclidean norm of WT. So this Poincare type inequality is precisely the one that is needed in the Lax-Milgram Fredholm or I should say Lax-Milgram Friedrichs theorem. And this can be established using integration by parts. So I will not discuss the proof of this inequality. So existence of weak solution to LIODE now follows from the Lax-Milgram Friedrichs theorem. How about the issue of uniqueness? Okay, one can show uniqueness as follows. So here, in fact, one can show that the image of the kernel of V is the whole space X. So it's not only dense, but in fact, it is the whole space X. Well, this is true if and only if, let's say, for every, let's say, F in L2, this is the space X. The ODE. So what lambda, take note that lambda is negative W prime plus A transpose W is equal to F in 0 to T. But of course, you need to take that W to be the kernel of phi. So this W must satisfy the condition that W of T is equal to 0. And from this ODE has a solution W in H1 0T N. So this equation here can be alternatively written or expressed as finding the solution of this backward in time differential equation. Because here, the data is now at the terminal time. Well, what you can do is, of course, after time reversal, so you reverse time so that the final time will be the initial time, and then apply for the existence. You can apply as well the Lax-Milgram Fredholm as well. So here, apply time reversal and the Lax-Milgram Friedrichs theorem to prove the existence of this solution. So this is what we call the dual problem for our impulsive ODE. So the application of the Lax-Milgram Friedrichs theorem for this linear impulsive ODE relies basically on this Poincare type inequality. And as I said, this can be established using integration by parts. This is called a Poincare type inequality since we have here, we have estimated the function in terms of its derivative. So that's one application of the Lax-Milgram Friedrichs theorem, establishing existence and uniqueness of weak solutions to linear impulsive ODEs. Well, the proof of this theorem is based on, obviously, the Lax-Milgram theorem and an appropriate extension theorem, which is the Hahn-Banach theorem. And that will be the topic for the next lecture.